Our topic for today is systems of linear inequalities. Over the past couple days, we've talked about linear inequalities, and we've looked at how to write the equations and graph them. We've seen that when we have a less than or greater than sign, the line that we draw is a dashed line. So we don't draw it as solid because the actual points on the line are not valid solutions. If we add the equal to part, then we draw it as a solid line, and then our line is a solution. We shade these based on the y values. If we have y is less than mx plus b, then we're going to shade below the line. And if we have y is greater than, we're going to shade above the line. And then our solutions are anything that's in the shaded regions. So we shade in where all of that solution set is. There's infinitely many solutions to one of these things, so everything in the shaded region is a solution. Today we're going to be talking about systems of linear inequalities, which is where we have two different inequalities, and we're looking for solutions to both of those. So solutions here will be in the shared shaded region. So it's basically we're going to have two of these graphed on top of each other, and any points that fall inside of the shaded regions of both will be our solutions. You may recall in probably last year you learned about systems of equations, and you might have a graph with two different lines. So you could have a line going this way, and then another line, say, going that way. And there's a point where those two lines cross. And all of the points along each line are solutions for that linear equation. But this point where they cross each other, where they intersect, is a solution to both lines. So with two lines, generally they cross at a single point, and you have one shared solution. But with these inequalities, we're going to have lots of shared solutions. So we'll see how that looks as we go through these. In our first example, we're going to go ahead and graph these two equations. This one, our x's are on the wrong side for y equals mx plus b. So first, to get into slope-intercept form, we'll move those x's to the other side by subtraction, and we'll get y is less than negative 3x plus 2. If we graph that, we go to plus 2, and our slope of negative 3, we go down 3 and right 1. And then, since this is a less than, we're going to put a dashed line. We're not going to put a solid line here. Remember that we still put arrows at the end of this dashed line to show that it goes on forever to the left and the right because there's no limitations to our domain and range that are given here. Okay, so then we have y is less than that, so we would shade this area over here below the graph. Our next equation or inequality that we have is y plus 1 is greater than or equal to x. That's also not in slope-intercept form. The 1 is on the wrong side, so we need to subtract it to bring it to the other side. And we'll get y is greater than or equal to x minus 1. We need to graph this as well. We'll start from minus 1, and then our slope is just 1 because it's 1 times x. So with the slope of 1, we're going to go up 1 and right 1 as many times as we want. And then, since this includes the equal to, we're going to draw a solid line for this one. All right, let's see all right, not bad. Okay, so we've got our line here, and in this case, y is greater than that, so it's going to be above it. So if I were to shade that in, it would be this area right here. Now what we're looking for with a system of linear inequalities is the solutions to both of these are where our shading overlapped. So if you're using a pencil, what you can do is just really lightly shade each of the two regions, and then wherever they overlap, darken that area in. You can also wait to shade it until you graph both of them and only shade the region that's in between the two and not get confused by having extra shading. So the part that we really care about here, I'm going to go ahead and highlight that, is this area over here that's where the two shadings overlap. So that is where all of our solutions to both equations lie. And if we pick any point over here, so let's go down to our list of points. If we look at 0, 0, our origin right here is in the double shaded region, so that will be a solution. 1, 4 is up here. It's in the green shading, but it's not in the blue shading. So this is a solution to one of them, but not both of them. 0, -4 is similar. It's in the blue region, but not in the green one, so it is not a solution for both. And then -3, 3, 1, 2, 3, 1, 2, 3 is right here, right in the middle of the double shaded region, so that is a solution for both of these linear inequalities. Or we would say it's a solution for the system. So we're doing basically the same thing that we've been doing the past couple of days with graphing these. The only difference is now there's 2 of them where there used to be 1. So I'm going to ask you to take a minute to try examples 2, 3, and 4 on your own. Pause the video, and when you're ready to go through them together, unpause it and I'll go over them with you. Okay, so this one, just like the others, needs to be rearranged. We need to move our 8x to the other side by subtraction. That will give us 4y is less than or equal to -8x plus 12. Then we need to divide everything by 4. At the end, we'll end up with y is less than or equal to -2x plus 3. So we get there just by our normal algebra steps of subtraction and division. Our second equation, which we'll draw in green here, is we need to subtract the 2. So we have y is less than 1/2 x minus 2. Let's graph those two. We have plus 3 as our intercept for the first one. We're going at a slope of -2. And this one, 1, 2, 1, 2, this one does include the equal sign. So we're going to draw a solid line here. And the area that we're going to be shading is below that line. I'm going to wait till I draw both of them and shade it for both together. So the second one, intercept at -2, slope of positive 1/2, so up 1, right 2. Looks like these are going to meet right here at this point. And then since this one has a less than, not a less than or equal, we need to draw a dashed line for this one. Still put arrows at the end. And what we're looking for is the area below the blue graph and below the green one. So the area that is common to both and would be our shaded area is going to be right here. That's below the blue and below the green. Next one we need to rearrange again. We get 2y is greater than or equal to 3x plus 2 by adding 3x to both sides. And then if we divide everything by 2, we get y is greater than or equal to 3/2 x plus 1. Our green function here, we're going to move the 4x to the other side and get y is less than 4x plus 3. Let's graph those two. So we go to plus 1, and then we have a slope of 3/2, so up 3, right 2, or down 3, left 2. This one includes the equal to sign, so we get to draw a solid line here, kind of off the point, but that's typical when I'm drawing on here. I can't draw straight lines with this tablet. So let's go draw the green one. We have 4x plus 3. 1, 2, 3. 4x would be 1, 2, 3. That would be off the graph, so let's go the other way. 1, 2, 3, 4, and 1. Looks like that's where they cross. And this one does not include the equal to, so we need to draw this as a dashed line. All right, we want to shade in the region that is above the blue graph, but below the green one. So that's going to be starting right here, and it's going to be this area. Let's do the last one, and then we'll look at these points and see which ones are included. Y is less than or equal to 3. That's an easy one because it's already in slope-intercept form. We want to go to y equals 3. And then this will be a horizontal line because there's no slope, there's no x term, and this one includes the equal. So we're going to draw straight across at y equals 3, and we're going to be looking for everything below that. The second one we need to rearrange by subtracting x from both sides. We get y is greater than negative x plus 1. Our intercept is here. Our slope is negative 1. And this one does not include an equal sign, so we need to make a dashed line for this one. And we'll put arrows at both ends. And then the region that we're looking for is below the blue line and above the green line. So below the blue line would be all of this, but then above the green is only going to be over here. So that is our shaded region. Now let's go back and look at the points for each of these examples. So on number 2, our solution 0, 0 is not a solution. 5, negative 1, 1, 2, 3, 4, 5, negative 1, that's not a solution. 0, negative 3, that is definitely in our shaded region, so that is. And then negative 2, negative 3. So that one is almost a solution, but since the green line is dashed and it falls right on the green line, that one will not be a solution because it's not included. We'd have to go a little further down to get into the solution set. On number 3, 0, 0 looks like it is not in our shaded region. 2, 4, 1, 2, 1, 2, 3, 4. That's this point right here. That's definitely in our shaded region. Actually, that's barely in our shaded region. So remember, I drew this line kind of poorly. It should be more like right here. So that's on the blue line. So since it's on the blue line, that is going to be a solution since the blue line is solid. So that one does fit. And remember, if you're ever unsure from the graph, you can always plug the point back into the equations or the inequalities and check it. So if we plugged in 2, 4 to the blue one, we would get 8 is greater than or equal to 3 times 2 plus 2, so that's 6 plus 2. 8 is greater than or equal to 8. That is true. And if we plug that same point in here, we would get 4 is less than, 2 times 4 is 8 plus 3. 4 is less than 11. That's also true. So that's a way of double checking if we can't be absolutely sure from the graph. But try to draw better graphs than I do here. Okay, so next point is 3, 5. 1, 2, 3, 1, 2, 3, 4, 5. That one's really hard to tell because of my poor drawing ability on this, so let's plug that one in as well. So 2 times 5 is 10, and we said that's greater than or equal to 3 times 3 is 9 plus 2. So 10 is not greater than or equal to 11, so that is not a valid solution. 0, 3, 1, 2, 3. That one falls right on our green line, and since our green line is dashed, that means it is not part of the green line solution set, so that one's a no. Our last one here, we have 0, 0. That is not a solution. 2, 2 is definitely a solution. 0, negative 4, definitely not. That's way below the green line. And then 5, negative 1 is definitely a solution. Okay, so that's how we would graph and evaluate solutions for these. Remember that these aren't the only solutions. There's infinitely many points here, and these lines keep going forever. So we could find points that are hundreds of units down the line, and they would still be solutions. All right, we have 2 more of that type of example. So again, try these 2 on your own. Make sure you understand how to work them, and then unpause the video once you're ready to go over them together. Okay, so y is less than 4x minus 3, conveniently already in slope-intercept form. So our intercept is here. Our slope is positive 4, so we go up 4 and over 1. This does not include an equal sign, so we're going to make a dashed line and do our best to follow these points. And then our green function here is y is greater than 4x plus 2. So we have a 2 here, 1, 2, 3, 4. We have the same slope of positive 4, meaning these two lines should be parallel. So we have basically 1 unit of horizontal space, or 1.5 units between these, maybe 2. Okay, so we are going to check these solutions. 0, 0. Oh, we didn't do any shading. So we're less than the blue line, so we're to the right of the blue line, and we're greater than the green line. Well, that's a problem because our blue shading would be here, and our green shading would be here. There's no overlap between those. Since there's no overlap, that means that there are no solutions that fit both of these equations or inequalities. So we can say that there are no real solutions. Or we could use this symbol that means the null set, where there's no numbers fall into that set. So none of these could possibly be solutions because there is no overlapped shaded region. On example 6, we have y is greater than x minus 2. So we'll put our y-intercept. We will go ahead and do that. So y is greater than that. So we don't have an equal to sign. We're going to do a dashed line. And then we're going to graph our second line. The green one is going to be x plus 4, 1, 2, 3, 4. And we have a slope of 1 again. So these two lines are also parallel. This one has an equal to sign, so we get to draw a solid line. And on this one, we are greater than the blue line, so we're above it, and we're less than the green line. So now we're going to be in this region that's sandwiched in between the two lines. So we will have a set of solutions along this diagonal that will continue forever in both directions. So let's look at our solutions. 0, 0, definitely in there. 1, 0, definitely in there. 0, 4, 1, 2, 3, 4. So that's right on the green line. And since the green line is solid, that is a solution. And then 8, 1 is going to be way over here. That's going to be below the blue line, meaning it will not be a solution. Since it's off the graph, if we're not positive that it doesn't work, remember we can plug it in up here. So we would get 1 is greater than 8 minus 2, and 1 is less than or equal to 8 plus 4. So we have 1 is greater than 6, not true. 1 is less than or equal to 12, that is true, but remember we're trying to make both of them true at the same time. Okay, so the next one we need to check whether a point is a solution to this system. We can easily do that like we just talked about by plugging in the x and the y value. So if we plug in x and y here, we get 0 minus 0 is less than 6. 0 minus 0 is less than 6. That's true. Then we would get 0 is greater than or equal to 0 minus 10. So that says 0 is greater than or equal to negative 10. And that's true because negative 10 is further left on the number line. So this is a solution because it fits both of our inequalities. Let's look at the next one. We have negative 1, 1. So if we plug in for the first equation, we get negative 1 plus 5 is greater than negative 10. So that tells us negative 1 plus 5 is 4, and 4 is greater than negative 10. Then if we plug in here, we get negative 1 minus 1 is greater than or equal to 4. So this says negative 2 is greater than or equal to 4. That is not true, meaning that this is not a solution for both of these inequalities. It's a solution for the first one, but not for both. All right, so here we have an example point that is given to us to see if it is a solution to the system of inequalities. We're first supposed to write the system using the graph as a guide. Remember to pay attention to the solid lines or dotted lines as to which symbol goes there for greater than or equal or greater. So I'm going to give you a minute. Do these three on your own. Make sure you understand them, and then you can unpause the video and I'll go through them with you. Okay, so let's do this as our first line and this as our second line. It looks like we're counting by twos here, and it looks like our y-intercept then is it looks like it's about 3. It might be slightly below 3. We probably need to go off of this point at negative 8, 0, and this point at negative 2, 2 to find out what our equation is. So let's do that in our blank space over here. So we have negative 8, 0, and we have negative 2, 2. If we calculate our slope, we would do y2 minus y1, that's 2 minus 0, over x2 minus x1, that's negative 2 minus negative 8. We get to change these two negatives into a plus. 2 over negative 2 plus 8, that's 6. So 2 over 6 gives us a slope of 1/3. Since our slope is 1/3, we could then use point slope form to find the equation. So let's do that. Let's use the negative 8, 0, and we'll do y minus 0 equals 1/3 times x plus 8. So that would be our point slope version using our slope of 1/3 and this point. Simplifying, we would have, and remember this is not an equal, sorry, I shouldn't put an equal. We have y and we have 1/3 x plus 8 over 3. So the intercept looks like it was actually 2 2/3, so a little less than 3. Our shading on this first line is above the line, and it's a solid line, so that means we have y greater than or equal to 1/3 x plus 8/3. For our second line, it looks like we are going at a slope of down 6 and over 2. 2, 4, maybe not. 2, 4, 6, 8. No, we're not hitting exactly on those points. But it looks like we have an x-intercept of negative 5. And it's tough to see what the slope is exactly. I see that it goes through negative 4, or at least very close to it. But not quite. That's tough. That's a tough one to just read from the graph. So let's just kind of guesstimate and say the slope looks like it's about, we're going down to 10 here, and so it's about negative 6 over 2, which is negative 3. So the slope is about negative 3x, and our y-intercept would be then at about negative 16. So if we went from, it looks like we're right about on this point, so if we went down, went over 2 more, we'd go down 6 more, so we'd end up down here at negative 16. Actually, negative 8. This is negative 9, isn't it? 4, 6, 8. No, that's negative 10. Okay. So let's just go with that. That's pretty close. This line, we're less than that line, and it's solid as well. So this will be a less than or equal to here. So the question, is negative 9 4 a shared solution? Negative 9 is right here, and 4 is here. So this is the point we're talking about. It is most definitely in our double shaded region, so that is a solution. So we don't need to go any further than that. If we needed to find another point, we could just pick any one that's over here. Okay, so try the other two on your own, see if you can find the equations or inequalities rather, and then check the point and whether it is a solution or not. When you're ready to, you can unpause and I'll go through it with you. Alright, so on this one, let's make this equation 1 and this equation 2. So for equation 1, we have a negative slope, we have a y-intercept of 4, so we have something plus 4. Our slope looks like it goes from a y-intercept of 4 to an x-intercept of 4, meaning it's going down 4 and over 4, which is a slope of negative 1. And we are shading above that line, and it's a solid line. So this will be y is greater than or equal to. For our second line, the one going uphill here, we don't have good y-intercepts or x-intercepts. We do see that it goes through this point at 2, -8, so let's capture that here. And it goes through this point where the two lines meet at 6, -2. So to calculate our slope, we'll do -8 minus -2, that's -6. And 2 minus 6, that's -4. So our slope here is going to be positive 3 over 2. Negative divided by negative, they cancel out. So our slope is 3/2. So we have 3 over 2x. We have y, and we know that on this line we're shading above that line as well, and it is a solid line, so this is also y is greater than or equal to. We just need to find our y-intercept, and it looks like if we're going down 3 for every 2 that we go left, we're going to go down to -11 as our intercept. Okay, so 6, -2, is that a solution? So 2, 4, 6, -2. We're talking about this point right where the two graphs cross. Since they're both solid lines, that would be a solution. But if even one of the two was a dashed line, this would not be a solution because it wouldn't be included with that one. Okay, number 11. We've got 2 more to figure out the inequalities for. Let's call this one on the left number 1 and this one on the right number 2. On the left, we have a solid line. The shading is to the right or above it. So if we go from this line, we're shading things that are above this line. And then that would mean we have a y is greater than or equal to something. I can see that we go 2, 4, 6, 8 down and 4 over. So our slope is going to be -8 over 4, which simplifies to -2. And then our y-intercept, that would be, did I count that right? 2, 4, 6, 8, 2, 4. Yes. So that means that our y-intercept should be, seems like it should be 4 down, yeah, -12. Okay, good. So we need to go down 4 more units and over 2, we'd hit right here at -12. Okay, second equation, we have an x-intercept of 1, it looks like, a y-intercept of -10, and we are below this line, so if we pick a point on the line, the shaded region is under that. So we're going to have y is less than, since it's a dotted line, dashed line, and we have an intercept of -10. It looks like our slope is going to be about -10 as well, because we were at -1 here, and then we went to 0 at our intercept. Or if we go this way, we go up 10 and over 1. So this will be -10x minus 10. Okay, our point 0, -4 right here is in the shaded region for line 1, but not for line 2. It's not in the overlapped shaded region. So this is a no. We could pick any point in here to be our point that we choose. I'm just going to pick -4, +4. That one jumps out to me as a nice, easy to pick one that's at an intersection of two of our axis values. So we'll say -4, +4 is a good solution, but there are infinitely many we could pick. So the homework assignment for today is very similar to the stuff that we've been doing as practice. You have some graphing to do, some rearranging of equations into slope-intercept form, some checking of solutions by graphing or by plugging in. So more practice of the same kind of stuff. So I'll let you work through those on your own. You can check with the key on Canvas.